Welcome to the study field. So today we will learn a topic from abstract algebra, that is group. Okay. So what is the definition of group? A non-empty set G is said to form a group with respect to a binary composition not. Here I denote this composition by the symbol not. Okay. So when a non-empty set G is said to be a group with respect to a composition when these four conditions are satisfied. That is, if G is closed under not, G is associative under not, and there exists an element E in G such that E not A equal to A not E equal to A for all A belongs to G, and for each element A in G there exists an element A dash in G such that A dash not A equal to A not A dash equal to E. So here as I read out this condition, G is closed under not, that means if we take an element A belongs to G, an element B belongs to G, then what we get? We get that A not B also belongs to G. This means that the set G is closed under this binary composition not. Okay. Now what about associative? Associative means if we take three element A, B and C belongs to G, then what we get? We get that A not B not C equal to A not B not C. That means the set G is associative under this composition not. Okay. And there exists an element E in G such that E not A equal to A not E equal to A. Means we have an element E that if we by left and right substitution of this element with respect to this composition, we get again the element A. Then what is the element is called? This element E is called the identity element. Okay. That means the group have an identity element also. Now again, for each element A in G there exists an element A dash in G such that A dash not A equal to A dash equal to E. And what is this A dash is called? This A dash is called the inverse element of the group. So if these four conditions are satisfied, then we can say that this is a group and we denote it by first bracket of G comma not. So there are some examples and non-examples in of groups. So example is Z comma plus, Q comma plus, R with respect to these composition plus, and set the set of complex number with respect to composition plus, and MZ with respect to the composition plus. So these are the examples of group. Now what are the non-examples? The non-examples are the set of natural number with respect to addition, the set of natural number with respect to multiplication, the set of integers Z with respect to multiplication, and the set of rational number with respect to multiplication, and the set of real numbers with respect to multiplication. So here the non-examples are more important than the examples. So in interviews many times they asked us what are the non-example of a group and explain why it's not a group. So here today I will explain why this structure or this composition with respect to multiplication M and N with respect to multiplication is not form a group. So here I take N with respect to multiplication. What is the first criteria to be a group? Is closed. So here I prove that the set here G equal to set of natural number and the composition not equal to X. Suppose and what is the set of natural numbers? Set of natural numbers mean 1, 2, 3, 4 dot dot dot. Okay. So this is the set of natural number. Now if I take any two elements, suppose I take 2 and 3, okay, belongs to set of natural number N. Now if I multiply these two elements, it is 2 into 3 equal to 6. So this 6 is also in this set N, so it belongs to N. That means the first condition is satisfied. Now coming to the second one, what is this? G is associative under the composition knot. Here what is knot? Here knot is multiplication. Suppose I take 4 and 4, 5 and 6. Okay, these are belongs to the set of natural number. Now if I take 4 into 5 into 6, what I get is equal to 4 into 5 into 6. That means that the second property is also satisfied, that is the n is the associative with respect to this composition multiplication. Now coming to the third one, here this is the identity property of a set. There exists an element E in G such that, suppose I take E into an element A. Suppose I take an element here, I take A equal to 4, belongs to natural number. Okay, so E into 4 equal to 4 into E equal to 4. So we can see that here what element we multiply with 4, that again we get 4. Here it should be 1. Okay, if I multiply 4 by 1, again we get 1. Similarly, equal to 1, E 1 into 4 is again we get 4. For any element n, A belongs to n, there is always the identity element is 1. So 1 is the identity here. So we can say that the third property of group is also satisfied. Now coming to the fourth one, what is this? For each element A in G, suppose I take an element 2 belongs to G. Here G means set of natural numbers. Okay, so here I take A in G, that is 2 belongs to n. There exists an element A dash in G. Suppose I take A dash as A dash belongs to natural number. Okay, in G such that A dash into 2 equal to 2 into A dash equal to identity. What is the identity here? Here the identity one is 1. So A dash into 2 equal to 1. What is the value of A should be? That the multiplication of A dash into is 1. So here if I take A dash equal to 1 by 2 and 2, then it is 1. So A dash is 1 by 2, but this 1 by 2 belongs to set of natural number? No, here set of natural number is the set of 1, 2, 3, 4, not the rational one, but is this 1 by 2 is a rational number. So 1 by 2 doesn't belongs to n. That means in this set n, in this composition set of natural number comma multiplication with respect to multiplication, where we didn't get any inverse of an element of natural number, set of natural numbers. So we can say that the fourth property is not satisfied here. So this composition in comma multiplication is not a group. Okay, thank you.